Welcome to the pre-recording of the first half of lecture 16 of our 8-week summer course, scheduled for the middle of week 6. So we are in the middle of our discussion on an iterative algorithm to compute maximum flow. And what we are doing in this lecture is we are going to reduce two problems to maximum flow. So the algorithm that we will be running will be the Ford-Fulkerson algorithm, which was introduced in the previous lecture. However, this lecture is mostly self-contained. It's mainly the concept of network flow that is important. So in the first half, we will do bipartite matching problem. So this is also the topic of this recording. In the next recording, in the second half of this lecture, we will discuss circulation. Okay, so bipartite matching. It goes back to the beginning of the course when we considered the stable matching. Here's a very simple example. We are given a bipartite graph where we can partition the set of all vertices into two disjoint sets. Typically, we draw such graph by placing all the vertices in the first set on one side and all the vertices on the other set on the other side. So there are only edges between these two sets. So we have that for any edge, the first element is always in the first set and the second element is in the second set. Then we define a matching as a subset of the set of edges where every vertex appears at most once. So we will consider the following optimization problem. We want to find the matching in this bipartite graph that is of the largest size. So we want to pick as many edges as possible. So here you see in this graph, the size of the matching is 3, but there is actually a matching that has that is perfect. We will illustrate this. Okay, what is an application? So we could think of job assignments. In one set are the workers, and in the other set are the jobs. And then having an edge between a worker and a job means that the worker can do the job to which there is an edge. Or it could be also a preference, but here it's either yes or no. Then the matching is such that we're looking for matchings, so every worker does at most one job, and workers are assigned only to those jobs that they are qualified for. So, and we want to do as many jobs as possible, and therefore it's also natural to ask for the matching in this bipartite graph that has the largest size. So often it is important and to look at a problem from many angles. So using the terminology of job assignments may sometimes help in understanding the problem. Okay, we can reduce this to a flow problem by adding a source and a sink. So the source is denoted by S and the sink is denoted by T. So, and we have as many outgoing edges out of our source to the first set, and the capacities of all the edges are 1. So when we compute a flow, we will work with integers. So it's actually either we assign a job to a worker or we don't. So that will be the virtue of working with integer numbers, that essentially we are computing true or false or 0, 1 values. So any bipartite graph can be transformed to a flow network. So we add a source and a sink, and then we keep all edges, but we work with the directed graph. So all the existing edges, we are going from the first set to the second set. We connect all the edges in the first set to the source. All the edges of the second set are connected to the sink, and all the capacities of the edges are 1. And this is a transformation. So the making of this graph G prime happens in linear time in the input size. So we need to run over all the nodes, over all the edges. And the number of edges that we add equals 2 times n, where n is the total number of vertices. So that is a transformation of one problem, the bipartite matching problem, into a flow network problem. So we will have to show that we indeed have a flow network. So the max flow essentially applies. So the graph that we constructed corresponds really with a flow network. And we have to interpret the solution that we compute with the algorithm of Ford and Fulkerson. So if we compute a maximum flow, does it give us then the largest matching in the original bipartite graph? Okay, how to relate matchings and flows? Well, if we have a flow, we have to go from source to sink. So we actually have to go from one vertex in the first set to a vertex in the other set. Then I'm actually now explaining the other way around. So it starts actually, the slide starts by saying, if you have a matching, that means that you have a set of edges where the first vertex in any edge starts in the first set. The second vertex in the edge belongs to the second element in that edge. So for all the edges in the matching that you select, we have a flow of 1 on that edge AB. The A is connected to the source, also with flow 1, and the second vertex in the edge, the B, is connected to the sink. So therefore, the value of the flow is the number of edges in the matching. Okay, so verify that the flow that we have defined here, so in our extended network G prime, we have a flow from source to sink. That flow is defined by a matching. I'm saying that it is a flow, so a flow assigns to every edge a value, a positive value. Now we have to show that the capacity conditions are holding, and that is by stating what is a capacity condition. Well, the flow is bounded by the capacity of the edge. Well, the flow that you assign is at most 1, and all the capacities are 1. So the first point of this exercise is therefore solved. And then you also have to show that whatever flow goes in also goes out. And for that, you need to use the property of a matching. So if you do have a matching, then you assign every vertex in the first set only once to every vertex in the second set. So that's a property that you have to use. So you have to use the properties of this specific network that we constructed for the bipartite matching, and you have to use the fact in your demonstrations. You have to use the fact that you have a matching. Okay, now the opposite. We have a matching, then we have a flow. That's the solution of exercise 1. So we, on the other way around, if we have a flow, then can we define a matching? So if we have a flow, we select all the edges of the original graph for which the flow is 1. So that is the definition of this M prime. So if the value of the flow is k, then the number of elements in that matching is also k. Okay, how are we going to show this? Well, we're going to use the optimality. So, and we will have, when the Ford-Fulkerson algorithm terminates, we can compute that follows from the optimality condition that there is a cut which actually separates the which partitions the graph. Now consider now the cut which separates the source from A. So if the value of the flow is k, that means that we have k edges for which there is flow, because every edge has capacity 1. So this is the incoming in A. And it also has to be the outgoing. So you have a one-to-one matching between the vertices that are in A and that carry flow. There are k of them, and they all have to reach the sink. So they all have to connect it to one of the corresponding vertices in the second set. So this is the observation by considering the example. We had the matchings that were given by the thick red lines. We could see that these matchings actually can be read off from the solution of the flow network. Okay, so if we have a flow, do we actually have a matching? And here again, the definition: given a flow, we select all the edges from the original graph, so for which there is flow. So this is actually the M prime is actually extracted from the flow network. But we will get the matching by eliminating the source and the sink. Okay, suppose that we have to show that this definition actually leads to a matching. So every vertex appears at most 1 times in our matching that is constructed, that is defined from the flow. Suppose that it would not be the case, so we will prove this by contradiction. Suppose that any vertex would be connected to 2 vertices. So this would give you a larger flow. Why not do that? Well, actually, this would then violate the contradiction, the conservation conditions. That's the solution of exercise 1. So what goes into one vertex is a flow of 1. And there cannot be a flow of 2 going out of that vertex. So that vertex cannot serve as a source. So this is for A. So for every vertex in A, it can appear only once. Also for vertex B, you can make the opposite picture. So where then you work by contradiction. Suppose that you would have 2 or more incoming edges in a vertex of the set B. That would then violate the conservation conditions, because that vertex is connected to the sink with with one edge of capacity 1. So you would have at least two edges coming in, both with flow 1, and then somehow the extra flow would need to disappear. But that cannot happen because we have a flow. The conservation conditions are respected. Okay, now actually I can define, given the m prime, we actually select those edges uh, from on which there is flow. And that actually defines the matching. So this theorem is is a direct consequence of the two lemmas. So the previous lemma stated that we had a matching. Okay, and the lemma before that stated that the number of elements in our m prime, so there is a direct one-to-one correction between m prime and m, that the number of elements in this m prime equals the value of the flow. Okay, so what we were after was actually the maximum flow. So if we have the maximum flow, then its value equals the size of the matching. So the corresponding matching is also maximal. So that's an important consequence. And so here we had properties of the matchings derived from the flow. But actually, are we sure that we do have the solution of our original problem? So one way to prove this would be to go by contradiction. Assume that your matching would not be maximal. That would mean that you could find one arrangement of the edges between A and B so that there is one more. So your matching M has K vertices. Well, suppose that it would not be maximal. Then you have K plus 1. You find one more edge. Then the contradiction will follow that if you have that one more edge, then you can define a flow. Then you can define a flow where the value is k plus 1. And this contradicts the if statement in this corollary where you said that the value of the flow is maximum. So it is k if the matching has k elements. So prove by contradiction. And it is essentially using the statement of the theorem and uh, de facto properties of the relationship between the matching and the flow. But since it is so important, it solves the original problem, we need actually it have proven. So the two exercises actually are very important. Okay, going back to the Ford-Fulkerson algorithm. So I said from the beginning, so my first example, it was actually not optimal. How can you see this? In some sense, this is an illustration of the Ford-Fulkerson algorithm in action. If you have skipped the previous lecture or you were still confused, here the Ford-Fulkerson algorithm is actually a little bit simplified because you have capacities that are all one. So in some sense, the capacities are redundant. So how does the Ford-Fulkerson algorithm work? Well, from the graph that we have obtained, so it's an iterative algorithm. So we have a solution that leads to a maximum flow of 3. Well, it's not the maximum flow of 3, because if you look at the residual graph, so on all the red edges where there is flow, we construct the backward edges because we want to reroute the flow. And if there is no flow, then we have a capacity of 1. So then we have forward edges. So on this residual graph here, we draw all the forward edges. And now I see that I still need to do some editing because there is here this edge, which actually is also part of the uh, forward edge. So there was no flow on the edge from 6 to 3. And however, it doesn't matter because what you see is that you cannot get to vertex 6. Um, so we compute an augmenting path, and in this application, this is called an alternating path. We can go from the source to the sink via an alternating path. And actually, um, it might be that I lied, that there is no such path. Um, let's look at this. So we can go from the source to 4, and then we can go from the source to 1, from 1 to 0, from 0 to 3, and from 3 to the sink. So it was not trivial. I had thought that I made somehow a capital mistake. But you see that we can reroute the sum of the flow, so we can actually augment. So on this alternating path, the value of the flow as 1. We defined that to be the bottleneck. And then we can assign here a flow of 1. So essentially reassigning, if you think of the job assignment, where at one side we have the um, workers and then the other side we have the jobs, we are reassigning the jobs. So worker 0 was assigned to job 1. We can give worker 4 job 1, and then we reassign the job 3 to worker 0. So you see that now we actually have a perfect matching. So one, in general, one sees this by computing the residual graph and observing that there is no path from source to sink. But here for this application, you can see that we have used all available edges leaving the source. We also have, and actually, if you compute the residual graph, you cannot leave the source. So that will be very quickly done. Okay, so I dwelled a little bit longer on this because this is kind of the essence of the Ford-Fulkerson algorithm, which makes the lecture more self-contained. Okay, and in some sense, the exercise 3 asks you to write out. So these were slides which were rather sparse, no text on it. So write the story of these calculations on the slides. In some sense, write it in your own words. And that will give you a good refresher of the essence of the Ford-Fulkerson algorithm. Okay, so what is actually the essence? We have shown that we can compute the maximum flow efficiently. So the algorithm with m edges and n vertices runs in time M times C, where the capital C is the sum of all the capacities. Now here, because the capacities are all 1, and we have in our assignment, so if we are computing the matching, we can have at most edges n edges that we select. So we have actually seen that the number of iterations that the Ford-Fulkerson algorithm does is bounded by the value of the flow. And if we have a very large flow and we work one by one by one by one, then it will take a very, very long time. That's why we had optimizations. We had the scaling parameter last time in the Ford-Fulkerson algorithm. This is not necessary here. So here actually we obtain a strongly polynomial time algorithm, as the running time cost in the Ford-Fulkerson, the m times c, is actually replaced by m times n. So the c depends on the size of the input numbers. So the original Ford-Fulkerson algorithm is therefore not strongly polynomial time, and there are also problems if we take real valued numbers for the capacities, if we take capacities that are real numbers. Here, the bipartite matching problem is in some sense a simpler problem. So finding a bipartite matching, actually the maximum matching, can be done in strongly polynomial time. So we have a reduction to the flow problem and we have a efficient solution. So that's actually the main result. Okay, so what if there is no perfect matching, which is bad if you have to schedule workers and you want to keep everybody busy. You kind of want to have somehow a proof, a certificate that no such perfect matching exists. And that then also gives somehow a way to fix, if you think about the job assignment problem, you may have to tell some workers that they do need to up their skills level so that they are able to do more jobs. Okay, what is a perfect matching? A perfect matching is when every vertex appears in the matching. And of course, this is typically, we now assume that we have as many elements in both sets of the partition. Otherwise, it will not work. So here we have the simplest example where that doesn't work. We have two vertices in the first set and only one in the second set. So here it is obvious that we can see this. But can we see something, can we, as a result of our computation, can we come up with somehow two workers which are in some sense qualified for only one job and who are not qualified enough for any more jobs? So I felt that when I was reasoning about the certificate, that the job assignment problem is actually quite helpful in phrasing the problem. Okay, what is a certificate? So we want to find a subset of the first set such that if we compute all the points they are connected to in the second set, that set is smaller. Again, you have too few jobs for which you have qualified workers. So the example, the certificate is the set of workers, so the first set, and then they are connected to the same vertex, so the cardinality is strictly less than the subset you began with. So this will consist, that will be your certificate. Now, it's always good to pause a little bit, and if you think about subsets, computing all possible subsets of the set A, we can do this if there are only 4 elements, because there are 2 to the power 4, and that's still finite. But 2 to the power n over 2, where n is the total number of vertices, grows exponentially. So you don't really want to do the brute force method by enumerating all possible subsets, even though the computation of this gamma is very straightforward. Okay, again, how come that this is a certificate? Well, here I have again the definition of this gamma for a subset. We are starting with a bipartite graph. So if actually so the intuition for this gamma definition is that if you have a perfect matching, any subset is actually connected to another subset that has exactly the same number of vertices. So, and if there is a perfect matching, then actually for any subset, you have that the number of connections is at least the set, the cardinality of the set you started with. So a matching again is a selection of the edges. So there you have a one-to-one correspondence. The definition, if ideally, if you think about scheduling workers to jobs, every worker is qualified for every job, so you don't have this problem if you have a versatile labor force. But in that case, any subset will be the cardinality of your gamma will always be the cardinality of B. Okay, so we actually want a certificate, so and that certificate will be a subset. It will be, but so here is the proposition. So if you read this proposition backwards, so if you take the negation of the then statement, so for all becomes there is a subset such that the cardinality of gamma is less than the size of the set S. So if that is the case, that's actually again the case where you had 2 points in A and they were connected only to one set. So if you have that, so you have this very simple situation, then indeed there cannot be a perfect matching. Is that actually true? So if this is the case, then you have no perfect matching. But if you have no perfect matching, can you come up with a set S? And even better, can you compute that set S? Um, so that will identify, that's a little bit similar to when we solved the maximum flow problem. We also identified a minimum cut. We actually identified those edges for which the flow equaled the capacity. And they were actually causing the algorithm to terminate, putting a limit on the maximum value of the flow. And we will see that to compute this certificate, you will actually have to look at the minimal cut as well. Okay, it's an important theorem. Whenever a theorem has a name, it has some importance. And what is important for us is that the proof is actually an algorithm. So the book, the textbook I'm following here, proves this, also saying this, but in some sense, if you know that there is a certificate, so here perhaps I should start by explaining the theorem and its relevance. So we know that if we have such subset for which we So we have the proposition that was read in the opposite way. Now actually we have either a perfect matching or we have a certificate that there is no perfect matching. Where when you give this set S, this subset S, you can immediately see, there are too few connections to the other set to get to a matching. And so this is a theorem that stands on its own, but in an algorithms course, we actually do have an algorithm that can be computed in strongly polynomial time. So, and it is the same bound. So we are interested in asymptotics here, and the big O comes always with a constant. It's not that you have to do a little bit more work, but it is of the same order. So very similarly that the max flow algorithm gave you the minimum cut, here actually you will have a certificate. And the certificate will actually use the cut. So here are the main ingredients in the proof. You compute the maximum flow, and we have shown last time that if you have the maximum flow, you also have a minimal cut. So, and the capacity of that minimum cut equals the value of the flow. Via a breadth first or a depth first search in the residual graph, you can actually compute all the vertices that are still connected to the source. And then by definition, the complement is actually the other set in that cut. And I will illustrate how you can actually compute that certificate from the cut. I will do this by an example. So here we have our running example again. We have a matching that is not perfect. I should say that it's our running example, but I removed one of the edges. So it's actually not the example. So it's an example where not every worker can be given a job. You can kind of see this here. Worker A1 is assigned to B1, and that's the only job that worker A1 can do. But then you have worker A3 that also can only be assigned to job B1. So there actually you see your certificate already. But let me now, so we see it, but let me now say how you can compute it. If you construct the residual graph, so this is the last step that you would do in the Ford-Fulkerson algorithm, then you will see that you can partition the vertices by looking for all the vertices that are still connected to the source. So these are the vertices, so you still have a path from source to A3 to B1 to A1, and then you start cycling back. So, and this is the only choice. So this is your first set in the cut, and then by definition, everything else is connected to the sink in this graph here. So that's the complement. Okay, so what do you do with this cut now? Well, actually it's the first set X that's important. You don't really compute the Y. So if you pick from the set X only the intersection with the first set A, so here in our, think about the job assignment, you have only the workers that you select, then you see that you get your certificate. So this is the systematic computation on this example. You identify the cut, and that is computed, can be computed typically very fast. The upper bound is the total number of edges that you can have. So, but if you have the cut after your maximum flow, you actually have a definition of the certificate. So this is the algorithm how to do it. And the point is the theorem says in time m dot n. Well, defining that set S is actually linear in the number of vertices. So the cut is bounded, the set X is bounded by n. So you're not going to do more than n steps. Um, okay, so there needs to be a proof that indeed you do have a certificate. So here is the statement. So we do have a bipartite graph without a perfect matching. And we have the minimum cut that is computed by the Ford-Fulkerson algorithm. Then our certificate is obtained by taking only those vertices from the first cut and that are in the first set in our bipartite matching. And then the claim is that if you compute the gamma, if you compute the set of all vertices connected to that subset S, that then you have fewer than there are elements in S. The proof actually follows the example. So if you have a matching with a flow equal to the cut, then it's not a perfect matching. So that's important. So there's at least one vertex, AI, that is not in the matching. So that's what it means to be no perfect matching. If you have that I mean not but AI, uh, that's not qualified for any job. So that's actually what means there is no edge. So that's an unfortunate situation. But then indeed you have your certificate already. So in that case, if there is no B that connects to I, well, you have a worker that cannot do any jobs. So that's actually your smallest certificate then. Now, otherwise, there should actually be another worker, another jade worker that is matched to that B. So B is connected to AI, but B is actually a job that is assigned to a J. Okay, if and there is and that actually implies that also you have your AI, you have your AJ, and you have your B already. So this actually shows that uh, you have this lesser of the cardinality because of the cut. If there is no such J, then actually AJ and B, so there is no B is actually not at all connected. But actually then AI, there is this edge to B, that would actually increase the flow by one. So this is the outline of the proof following the reasoning from the example. Okay, one last exercise, thinking about this problem. In most cases, uh, you can say you can assign more than one job to each worker. Um, so what if the workers can do more than one job? Essentially, you might be able to run the bipartite matching problem multiple times, scheduling the jobs in rounds, if you like. But you can also do this by modifying the problem. And if you think about, so you have two sets now. You have M workers and N jobs. Typically, you have more jobs than you have workers. So you could think about having added the source is that if every worker can do only one job, you kind of give it an edge with capacity 1. So you can interpret that edge as kind of the resources that you give for completing a job. So you could interpret that as the so you could actually assign more sources as well. So that could be another way of seeing this. So you can set up a flow network so every worker can do up to 3 jobs. So instead of having capacity 1 from source to workers, you have 3, the value 3 there. Now, does this define a flow? That's then what you have to decide, that you have to prove, verify the capacity conditions. You would still have 1 for all the connections. So every worker spends 1 unit of flow to do a job. And since there are more jobs than workers, you would still have that everything that leaves the source. So typically in a perfect matching, although it shouldn't be perfect matching, but in a perfect matching, you would have 3 times the number of vertices in B than you would have vertices in A. And by the conservation laws, everything that leaves the source would also enter in the sink. So you have to show that the maximum flow will give you an assignment that can be interpreted as a flow and as a matching. So the Ford-Fulkerson algorithm applies to this problem. Again, you have to do some reasoning here. It is important, again, that we work with integer numbers. So does the Ford-Fulkerson apply to this problem? Figure out an example with 2 workers and say 5 or 6 jobs and explain how this works. Okay, that was the first half of the lecture where we considered the bipartite matching problem. It is a problem that is very similar to the first problem that we started with, so that was the stable matching problem. Um, the Ford-Fulkerson algorithm is actually quite versatile, and here actually we solved a very similar problem than the stable matching problem, except that we didn't use preferences here, but we also found a very efficient algorithm for it that runs in strongly polynomial time. In the second half of this lecture, we consider another application and we'll decide the feasibility in a circulation problem.